Hello everyone! In today's lesson, we'll learn about limits at infinity. We'll look at what a limit at infinity is and how this new type of limit can be evaluated graphically and analytically. At the start of your lesson, you had the pre-video activity, horizontal asymptotes. If you haven't had a chance to work on it yet, pause the video to do that now. Let's work it out together. In the pre-video activity, we were given the equations and graphs of three functions, a, b, and c, and had to first identify any horizontal asymptotes. Remember, a horizontal asymptote is a line the graph approaches as it extends forever to the right or forever to the left. Function a seems to have a horizontal asymptote at the x-axis or y equals 0. Function b seems to have a horizontal asymptote at y equals 2. What about function c? Does it approach a horizontal line on either end? It doesn't seem like it. Therefore, function c doesn't have a horizontal asymptote. The second question asks, how could we have determined the horizontal asymptotes by just looking at the equations of the functions? These three functions are all rational functions. Back in Unit 2, we learned how to find the horizontal asymptotes of rational functions based on the degrees of the numerator and denominator. In function a, we have a quadratic polynomial over a cubic polynomial, so a numerator degree 2 and a denominator degree 3. How do these degrees result in the asymptote at y equals 0? As x increases to infinity, either positively or negatively, the cubic denominator grows faster than the quadratic numerator, causing the quotient to get smaller and smaller towards 0, which makes the function approach 0 on both ends. This is why, in general, for rational functions, every time we have a greater degree in the denominator, there will be a horizontal asymptote at y equals 0. How about function b? The degrees of the numerator and denominator here are equal. They are both cubic. As x grows larger and larger, these leading terms become super large, making this constant term of 1 become less and less relevant, which makes the function increasingly closer to just being 10x cubed over 5x cubed, which simplifies to 2. This is why there is a horizontal asymptote at y equals 2, and why every time we have equal degrees, the horizontal asymptote becomes the ratio of the leading coefficients. Finally, what made function c have no horizontal asymptote? The degree of the numerator was larger than the degree of the denominator, which means that the quartic numerator grows faster than the denominator, which results simply in a larger and larger quotient as x increases positively or negatively. This is why every time the degree of the numerator is larger, the function has no horizontal asymptote. Now that we've identified horizontal asymptotes for these functions, let's connect that to limits. In fact, the limit at infinity helps us describe these asymptotes formally. Let's see how that works. Here's the notation we use to describe the end behavior as we go forever to the right and approach a finite value, which is read as the limit of f of x as x approaches infinity equals L, and means f of x approaches the finite number L as x gets larger and larger. Similarly, we use this notation to describe behavior as we go forever to the left, which is read as the limit of f of x as x approaches negative infinity equals L, and means f of x approaches the finite number L as x gets larger and larger in the negative direction. Now, remember, even though we're talking about approaching infinity, The positive and negative infinity symbols do not represent numbers. They're simply communicating x increases or decreases without bound. Let's use limits at infinity to describe the end behaviors of these functions. For example, since function a goes to 0 as we go forever to the right, the limit of a of x as x approaches positive infinity is 0, and so is the limit of a of x as x approaches negative infinity, because the function approaches 0 on the left end as well. Pause the video and write the end behavior of functions b and c using limits at infinity. Let's check your work. The limit of b of x as x approaches positive infinity and also the limit as x approaches negative infinity are both 2. What about function c? Since the graph doesn't approach any finite value on either end, both the limit of c of x as x approaches positive infinity and as x approaches negative infinity do not exist. That said, we can be a bit more specific with our answer by writing that the limit as x approaches positive infinity is positive infinity because the graph goes forever up on the right end, and that the limit as x approaches negative infinity is negative infinity because the graph goes forever down on the left end. Notice that there is a very tight relationship between the horizontal asymptotes and the limits at infinity. In fact, here's the formal definition of a horizontal asymptote. The line y equals L is a horizontal asymptote of the graph of f if either the limit of f of x as x approaches positive infinity is L, or the limit of f of x as x approaches negative infinity is L. This was exactly what happened with the functions in the pre-video activity. When the limits at infinity existed, there were horizontal asymptotes at those values. But when the limits didn't exist, there were no horizontal asymptotes. Now, let's see how to evaluate limits like these analytically without the need for the graphs or even the rules for horizontal asymptotes. Firstly, let's find some key limits at infinity that will be the building blocks to help us evaluate more complex limits. Let's start with the limit of 1 over x as x approaches positive infinity and as x approaches negative infinity. Here's the graph of 1 over x. We know this graph has a horizontal asymptote at y equals 0 because dividing 1 by larger and larger positive or negative numbers reduces the quotient towards 0. Therefore, both these limits are 0. Now, from these limits, we can derive some more general limits that will prove very useful later. Limits at infinity follow the same laws as other limits. We just replace the a with the positive or the negative infinity symbol. Let's find the limit as x approaches positive or negative infinity of 1 over x to any positive integer power k, which is the same as the limit of 1 over x to the k. Using the power law, we can rewrite this limit as the value of the limit of 1 over x to the power of k, which we know is 0, and 0 to the power of any positive integer is just 0. From this limit, we can also find the more general limit for when the numerator is any real number c, not just 1. We can rewrite the c as a constant multiplying 1 over x to the k, and then use the constant multiple law to pull out the c. We know the limit of 1 over x to the k is 0, and any real number times 0 is once again 0. So in general, the limits at infinity for functions of the form c over x to the k, where k is any positive integer and c is any real number, are 0. What about the special limits we had? How do they look for limits at infinity? Let's look at the first 3 since they will be the most useful to us for both positive and negative infinity. For a constant function c, which is just a horizontal line at c, as we approach both positive and negative infinity, the function continues to approach c because, well, it stays at c. For the linear function x, which is a line with slope 1 through the origin, as we approach positive infinity, the function grows to infinity, and as we approach negative infinity, the function goes toward negative infinity. Remember, these limits do not exist, but it is useful to have in mind whether they go to positive or negative infinity. For the general power function x to the n, let's look at the graphs of some power functions. What do you notice as x goes to positive infinity? It looks like all the curves go to positive infinity. But what about when x goes to negative infinity? It seems we have two separate cases. When the degree is even, the curves go to positive infinity. But if the degree is odd, the curves go to negative infinity. Now let's put everything we've learned to work. Let's look at the limits at positive infinity for the three functions from the pre-video activity, but now we'll evaluate them analytically. Our main strategy to evaluate limits at infinity of rational functions will be to divide numerator and denominator by the highest power of x in the denominator. This might seem strange, but let's walk through the process together, and then you'll see why this helps us find the limit. In the first limit, the highest power of x in the denominator is x cubed, so we're going to divide numerator and denominator by x cubed. Simplifying this expression, we get 10 over x over 5 plus 1 over x cubed. Why is this strategy helpful? Dividing by the largest power of x in the denominator helps us identify which terms grow the fastest as x becomes very large. Then, using the limit laws, we can break the limit into simpler limits that are easier to evaluate. These two limits are of the form c over x to the k, so we know they are equal to 0. According to our special limits, any limit at infinity of a constant is equal to the constant itself. So this limit equals 5, and 0 over 5 plus 0 equals 0. This result perfectly matches with the horizontal asymptote of the function at y equals 0. On your own, evaluate these next two limits analytically using the same strategy. Pause the video now. For limit b, once again, we divide by x cubed since that's the highest power in the denominator, and simplify the result. Then we can use the limit laws to break the limit down into simpler limits and evaluate each using the limits we know. We get the expected result of 2. For limit c, we'd still divide by x cubed and simplify the expression to 10x over 5 plus 1 over x cubed. Now, before breaking apart this limit with the limit laws, we need to be sure the limit of each component actually exists. We know 1 over x cubed goes to 0 as x goes to infinity, so the entire denominator goes to 5 plus 0, or 5. However, what happens in the numerator? As x goes to positive infinity, 10x will also go to positive infinity. So if our numerator goes to positive infinity and the denominator goes to 5, where does the entire quotient go? Dividing by positive 5 doesn't affect this end behavior, so it still goes to positive infinity. Now let's look at these two limits at negative infinity. Evaluate these analytically on your own. Pause the video now. In the first limit, we divide numerator and denominator by x cubed and simplify the result. With limit laws, we can evaluate this limit by finding the limit of each separate term, since those limits all exist. We get 18 over negative 6, which is -3. Now the second limit. We divide numerator and denominator by x to the fourth, which is the highest power in the denominator, and then simplify the result. As x approaches -infinity, both these terms go to 0, and the 2x squared, due to the even degree, goes to +infinity. Therefore, the entire numerator goes to +infinity, and the entire denominator goes to -1. Because of the division by -1, this quotient ends up going to -infinity. Let's wrap up this lesson with these two limits. Based on what you know about trigonometric and exponential functions, try to figure these out on your own. Pause the video now. Here's the graph of the sine function. What happens as x approaches infinity? We know the sine wave will continue to oscillate between 1 and -1 infinitely, so the function doesn't approach any finite value. Therefore, the limit doesn't exist. Notice how, unlike previous non-existent limits we've seen, here we can't write infinity or -infinity due to the oscillating behavior. We can only say dne. Now let's look at the graph of the exponential function e to the x. What happens as x approaches -infinity? We know this function has a horizontal asymptote at y equals 0 because, specifically as x decreases without bound, the function approaches 0. Therefore, this limit is 0. Today we learned a lot about limits at infinity, which are limits that describe the end behavior of functions as x gets infinitely large in the positive or negative direction. We used these limits to formally define horizontal asymptotes and learned a very useful strategy to find limits at infinity of rational functions, which involves dividing numerator and denominator by the highest power of x in the denominator. Once you've finished your guided notes, complete the additional practice. After that, make sure to complete the online practice. See you next time! Hey, hey.